In this lesson, we're going to talk about polynomial functions. A polynomial function is a function of the form f of x equals an x to the n plus an x to the n minus 1, etc., all the way down to plus a naught, where a naught, a1, a2, etc. are real numbers and n is a whole number. It's easy, or it's perhaps easier to see what they are when you see some examples. Y equals 7x squared plus 3x minus 1 is a valid example of a polynomial function because all of the integers are, all of the exponents are non-negative integers. We've got x to the 1, we've got x to the 2. Even here, the constant term, we've got x to the 0. Y equals negative 55x, 55 over 2x to the 9 is also a valid example. And y equals negative 14x to the 11 plus 2x to the 13 minus 8x plus 2 is a valid example. It's okay in a polynomial function to have a constant term. Non-valid examples include y equals 4x squared plus x to the 1/2. We cannot have non-integer exponents in a polynomial function. Or negative 7x to the 9.5. Again, we cannot have non-integer exponents. How about 3x plus 4x to the negative 1? Well, there's a negative exponent there. We cannot have that. And we certainly cannot have a term like sine x in a polynomial function. So the order of a polynomial function is important to know. The order is the largest exponent on x in the function, and this is also sometimes called the degree. So in the polynomial function y equals 7x squared plus 3x minus 1, the order is 2. In the polynomial function negative 55 over 2x to the 9, the order is 9. In the third polynomial function shown, the order is 13 because we have to just make sure that we have the exponents in the correct order, descending order. In the polynomial function y equals 5x plus 2, the order is 1. And in the polynomial function y equals negative 7, the order is 0. We don't usually think of this as a polynomial function. Now, the lead coefficient of a polynomial function is the coefficient in the term with the largest exponent on x. So in the example y equals 7x squared plus 3x minus 1, the largest exponent on x is 2, and so we would say the lead coefficient is 7. In the second polynomial function shown, the lead coefficient is negative 55 over 2 because that's the coefficient in the term with the largest exponent on x. In the third function shown, the lead coefficient is 2. Make sure we rearrange so the term with the greatest exponent is first. In the fourth example, the lead coefficient is 5. And finally, the lead coefficient is negative 7 in the last example. As we said, we don't usually think of this as a polynomial function, but technically it is. Now, let's talk about the end behaviors of a polynomial function. There's a helpful relationship between the order, the lead coefficient, and the end behaviors of a polynomial function. Now, I'm going to just jump forward a few slides and get right to the point, and then we'll show you why this is true. If you have an even degreed function with a positive leading coefficient, the end behavior will be as shown here. As x goes to negative infinity, y will go to infinity, and as x goes to infinity, y will go to infinity. So the end behaviors will be up in the first and second quadrants. If you have an even ordered function and a negative leading coefficient, our end behaviors will be in the third and fourth quadrant. So an example of the first type would be this polynomial function right here. If we say y equals 5x to the 4 plus 7x plus 1, then we say that the lead coefficient is 5 and the order is 4. So we've got a positive lead coefficient of 5 and an even order of 4. And because of that, we know the end behavior. If we look at the second example here, the lead coefficient is negative 11 and the order is 6. We've got a negative leading coefficient and an even order. And when we have that, we know what the end behavior will be. In the third example, if we have an odd order and a positive leading coefficient, for example, this polynomial function here, where the leading coefficient is 6, in other words, positive, and the order is 5, in other words, odd, when that happens, our end behavior will be in the first quadrant and the third quadrant. And finally, if we have an odd order and a negative leading coefficient in a polynomial function, for instance, a function such as y equals negative 2x to the 7 plus 14x squared, if this happens, then we would say our lead coefficient is negative and our order is odd. And then we know that our end behaviors will be in the second and fourth quadrants. So this is a very helpful relationship when it comes to knowing the behaviors of polynomial functions. The first thing that is easiest to see are the end behaviors. Now, it's important for you to know this table very well. Let's go back a few slides and just sort of establish why these are the way they are. Imagine the functions y equals x and y equals x cubed. We can think of x as x to the 1 and x cubed. In both cases, the lead coefficient is 1. In other words, the coefficient in front of x to the 1 or x cubed is 1. And in both cases, the degree is odd. In the first case, the degree is 1, and in the second case, the degree is 3. Well, if we look at the function y equals x to the 1, we see that our end behaviors are in the first and third quadrants. And if we look at the function y equals x cubed, we see that the end behaviors are in the first and third quadrants. And that is what we said it would be in our table a few slides forward. Now, going back, let's take a look at what would happen if we had the functions y equal negative x and y equal negative x cubed. In both of those cases, the lead coefficient is negative 1, and in both of those cases, the degree is odd. So if we have a negative leading coefficient and an odd degree, our end behaviors will be in the second quadrant and the fourth quadrant in both of these cases. And it will always be that way, as we indicated in that blue table a few slides forward that we've been looking at. Whenever the order of a polynomial function is odd and the lead coefficient is negative, the end behaviors of the function are as x goes to negative infinity, y goes to infinity, and as x goes to infinity, y goes to negative infinity. Now, what if we have an even degreed function? For instance, y equals x squared or y equals x to the 4. In both of those cases, we have a positive leading coefficient and an even degree. When that combination of things happens with a polynomial function, our end behaviors are in quadrant 1 and quadrant 2. And we get the end behaviors shown there. And finally, when we have the functions y equal negative x squared and y equal negative x to the 4, we've got negative leading coefficients and even degrees, and our end behaviors are in quadrant 3 and quadrant 4 in both cases. Now, the reason we go through those examples is that for some people, these should be negative infinities here. The reason we go through those examples is that for some people, rather than memorizing this table, they can just memorize what happens in the most easy to remember examples of each type of polynomial function. So the functions y equal x squared, negative x squared, x cubed, and negative x cubed are easy for most students to remember. And if they can remember how to sketch a graph of those, they'll then know for sure, without having to memorize this table, what the end behaviors will be for any polynomial function that they're faced with. Now, the reason that we only have to consider the sign and exponent of the term with the highest exponent when discussing end behaviors is that as x approaches an infinitely huge value, the impact of the terms with lesser exponents become less and less. As x heads to negative infinity or positive infinity, the term with the largest exponent on x dominates the value of y more and more. As an example, consider the function y equals 2x to the 5 minus 100x to the 4. Now, if we have x values around the origin, for example, an x value of 1 or 2, the value of y will be dominated by the term negative 100x to the 4. But if we sub in a value for x of, say, 1 billion or negative 1 billion, the impact of the negative 100x to the 4 term will be far, far less than the impact of the 2x to the 5 term. So end behaviors are behaviors that occur as x gets infinitely huge, either the magnitude of x gets infinitely huge, either to the far left or the far right. So the impact of the second term is negligible. So we can just basically focus on that lead term. Now, what would be an example of a question? If I said to you, what are the end behaviors of the function y equals 7x to the 5 minus 12x squared plus 7? Well, you don't need to actually graph that curve in order to know what its end behaviors are. What you can do is you can look at it and say, okay, this is a polynomial function. It has a positive leading coefficient. The leading coefficient is 7, and it has an odd degree. The degree is 5. Whenever a function has a positive leading coefficient, whenever a polynomial function has a positive leading coefficient and an odd degree, its end behavior is the same as the end behavior of the curve y equals x cubed, which also has a positive leading coefficient and an odd degree. And so we can say, to answer this question very quickly, if it was asked on a test, we could say that the end behavior is as x goes to negative infinity, y goes to negative infinity, and as x goes to infinity, y goes to infinity. Okay, now what about the nth finite differences of a polynomial function? Suppose, for example, we were given the function y equals 3x squared plus 2x minus 7. This is degree 2 because of the exponent 2. Suppose I said to you then, okay, it's degree 2. What can you tell me about the second differences? Well, what we could do is make a table of values, and then we could determine our first differences by subtracting up on all these y values. Negative 6 minus 1 is negative 7. Negative 7 minus negative 6 is negative 1. And we could continue through the entire table. Then we could, after getting our first differences, we could then determine our second differences. So we would do that by subtracting up. Negative 1 minus negative 7 is 6. 5 minus negative 1 is 6. 11 minus 5 is 6, and 17 minus 11 is 6. And lo and behold, we would see that the second differences of a degree 2 polynomial function are constant. Well, let's see if we can see a pattern developing. What if we were given a degree 3 polynomial function? And then I said to you, okay, it's degree 3. Tell me about the third differences. Well, we could figure out the first differences, and in this case, by building a table of values with x's and y's. In this case, the first differences would be given by all these values here. Then we could make a second differences column, subtracting up in the first differences column. And if we did that, we would get these values here for the second differences. Then if we find the third differences by subtracting up on the second differences, we would see that the third differences are constant. Okay? And so that is a characteristic of polynomial functions. Specifically, the nth finite differences of a polynomial function of degree n are constant. So the second differences of degree 2 polynomial function are constant. The third differences of a degree 3 polynomial function are constant. Fourth differences of a degree 4 are constant, etc., etc. Other characteristics of polynomial functions. The domain of all polynomial functions is x element of the reals. This makes sense because any value of x can be plugged into a polynomial function. Because remember, there are no fractional exponents, which means there are no radicals, no square root signs to worry about, not being, not letting x be negative because of that. We don't have to worry about that because there are no fractional exponents. There's also no negative exponents, so we don't have to worry about x values in the denominator. So the domain of all polynomial functions is x element of the reals. The range of all polynomial functions with an odd degree is y element of the reals. Now this makes sense. If we have a polynomial function with an odd degree and a positive leading coefficient, our n behaviors is as shown. Now, the curve might do some fancy turning in the middle, but it's ultimately going to go down to negative infinity in terms of the y value and up to positive infinity in terms of the y value. So if it's an odd degree function, the range is guaranteed to be the set of all y element of the reals. But what happens to even degree functions? Well, if the lead coefficient's positive, then the n behaviors are as x goes to negative infinity, y goes to negative infinity, and as x goes to infinity, y goes to infinity. In other words, the n behaviors look like this. Well, both of these n behaviors are pointing up, which means that the curve might turn and twist in the middle, but it's ultimately going to be up on both ends. So there's going to be an absolute minimum somewhere. Somewhere in such a situation, there will be an absolute minimum value for y. And so what that means is that the range will be y element of the reals such that y is greater than or equal to a for some value of a. And if the lead coefficient is negative and it's an even degreed function, polynomial function, then our n behaviors look like this. Well, in between those n behaviors, the curve might go up and down and have different turning points, but both of the n behaviors point down. Somewhere there's going to be a maximum possible value for y, and we call that an absolute maximum value for y. And when you have an absolute maximum value, that means the range is the set of all y element of the real such that y is less than or equal to b for some maximum y value of b. This word here should say maximum. Okay. Now, another characteristic of polynomial functions is that they all create smooth curves which might have turning points. All of these are examples of polynomial functions. They're smooth, they have turning points, they have acceptable n behaviors. Now, in this case, the n behaviors, in the first case, our n behaviors are in quadrant 3 and in quadrant 1. That tells us it's an odd degree function with a positive leading coefficient. In the second case, our n behaviors are in quadrant 2 and in quadrant 4, and that tells me that there's an odd degree function, but this time with a negative leading coefficient. In the third example, we have n behaviors in quadrant 3 and in quadrant 1, much like we did in the first example. And so again, it's a different function, but just like in the first example, it will be an odd degree function with a positive leading coefficient. And in the fourth example shown, our n behaviors are in quadrant 3 and in quadrant 4. So we know we've got an even degree function with a negative leading coefficient. Now in that first example, we have two turning points. A turning point occurs when the function goes from an increasing to decreasing interval or from a decreasing to increasing interval. There's a turning point in each of these cases. So the first example has two of those turning points. The second example has none. The third example has 4 turning points, and the fourth example has 5 turning points. So a turning point looks like either a hilltop or the bottom of a valley. An even degree polynomial function will have an odd number of turning points, at least one and at most n minus 1. So for example, if I have a polynomial function of degree 8, there will be 1 or 3 or 5 or 7 turning points. An odd degree function, a polynomial function, will have an even number of turning points, possibly 0 and at most n minus 1. So a polynomial function of degree 9 would have 0, 2, 4, 6, or 8 turning points. An even degree polynomial function might have anywhere from 0 to n x-intercepts. So for example, if I say I have a polynomial function of degree 6, there might be 0, 1, 2, 3, 4, 5, or 6 x-intercepts. Now you might say, my gosh, how could there be 0 x-intercepts? Well, remember, our n behavior, if it's an even degree polynomial function, could look like this. And if it does, it's possible for us to have turning points and never cross the x-axis. Or even if the n behavior is down here, it's possible for there to be, even if there are turning points, it's possible for there to be no x-intercepts. Okay? Now, an odd degree polynomial function, however, in the second half, that must have at least one x-intercept. The reason being, if we have an odd degree polynomial function, we see from our n behavior that we must be crossing the x-axis at least once. Or if we have a negative leading coefficient with an odd degree, we must be crossing the x-axis at least once. It's impossible to get from one x-axis, from one n behavior to the other without crossing that x-axis. So if it was degree 5, we could have 1, 2, 3, 4, or 5 x-intercepts. Okay? Polynomial functions have no asymptotes and are continuous over all x element of the reals. So here's an example. State the degree, leading coefficient, and n behaviors of the function shown. Then state the possible number of turning points and possible number of x-intercepts. Okay, well, first thing I do is I say my lead coefficient is -2 and my degree is 5. Because I have a negative leading coefficient and a odd degree, I know exactly what my n behavior is because I remember that table from earlier. Or even better, I remember what a really simple version of a polynomial function with a negative leading coefficient and odd degree looks like. Specifically, I remember what y equals -x cubed looks like. And since y equals -x cubed has a negative leading coefficient and odd degree, it must have the same n behavior as this more complicated looking function with a negative leading coefficient and an odd degree. Now, because the degree is 5, I know that there must be 0, 2, or 4 turning points. And because the degree is 5, i.e. odd, I know I can't have 0 x-intercepts, so I must have 1, 2, 3, 4, or 5 x-intercepts. Let's state the degree, leading coefficient, and n behaviors of this polynomial function. Well, what's a little bit tricky about this is the terms are stated out of order. Our lead term is this one right here. So we've got a positive leading coefficient and we have a odd degree. Okay, so now that we know that, we see that the lead coefficient is 8, the degree is 7, and it's easy for us to determine what the n behaviors are. Now there might be, because the degree is 7, there might be 0, 2, 4, or 6 turning points. And because it's odd, we know there can't be 0 x-intercepts, so there must be 1, 2, 3, 4, 5, 6, or 7 x-intercepts. Why don't we state the degree, leading coefficient, and n behaviors of the function shown? Well, we don't have to expand this polynomial. The lead terms of each bracket and the factor of -4 in front combine to give a lead term of -8x to the 4. In other words, just take this -4, this 2x, this x, and this x along with this squared, so this is kind of like an x squared. So let's multiply those, a 4 and a 2x and an x and an x squared, and multiply those out. And when you do that, you get, oh, sorry, this should have been a -4 in front. And when you do that, you get -8x to the 4. That tells me that the lead coefficient is -8 and the order is 4. From that, I can tell you what my end behavior is. I can tell you that there might be 1 or 3 turning points, and I can tell you how many x-intercepts there might be based off of based off of the knowledge of the degree of the function. Now, as a quick little aside, to tell you the truth, we know exactly how many x-intercepts there are here. There are 3 x-intercepts, because we could say x is equal to 3 halves, gives us 1 x-intercept. We could say x equals -1, gives us another x-intercept. And we could say x equals 3, gives us another x-intercept. So we actually know for a fact that this function has 3 x-intercepts. But if we were to, without going that far into it, if we were just to look at the lead term without looking at the factored form of it, based off of the lead term, we would say there were 0, 1, 2, 3, or 4 x-intercepts, even though we know there are exactly 3. We're going to determine whether the degree of this function is odd or even, and whether the lead coefficient is positive or negative. Well, based off of the end behavior, we can say the lead coefficient is negative and the degree is odd. Must be, because our end behavior is in quadrant 2 and in quadrant 4, and we recall what our table told us a while ago. Let's sketch a polynomial function with a degree of 6, a negative leading coefficient, and 5 turning points and 3 zeros. Okay, well, we have an even degree and a negative leading coefficient, so we know that our end behaviors are going to be in quadrant 3 and quadrant 4. In graphing this curve, we are going to start by putting the end behaviors down first. Now, if we have 5 turning points, we could draw the curve like this. We have 1, 2, 3, 4, 5 turning points. So far we have degree 6, we have a negative leading coefficient, and we have 5 turning points. We're doing all right. The problem is it only wants us to have 3 zeros, but we have 1, 2, 3, 4, 5, 6 zeros. So we have to somehow reduce it. So what we can do is just move one of those turning points. See this turning point on the far right here? We're just going to put that below and now count our zeros. Well, we're getting closer to 3, but unfortunately we still have 4 zeros. So what we can do now is we can move the second one below as well. That second, this turning point right here, we can move it below. But now we've only got 2 x-intercepts. So that's too bad, because we wanted there to be 3 zeros. So what we're going to do now is we're going to put one of our vertexes, one of these turning points, we're going to put it right on the x-axis. So let's count the turning points. We have 1, 2, 3, 4, 5. So that's good. And let's count the zeros. We've got 1 0 right there, 2 zeros, and 3 zeros. So we've actually met the conditions required in the question. And that is the end of that slideshow.